be equal. When
जब
Q
दोनों
is, the
बराबर
contents of Q and P are equal. So when these are equal, so actually Q minus P will be 0. When Q minus P will be 0, the flag will be 1. The branch will be taken if Z is equal to 1. And the branch will not be taken if Z is equal to
0.
The branch will be taken when C is equal to clear 0, when C is equal to 1. Carry clear, carry set. V is equal to 1, V is equal to 0. I will explain this with an example. Now let's assume a scenario. We say that compare R3, R2, and then branch equal label, and then this is the label. If the contents of R3 and the contents of R2 are 5 and 5, so we are comparing R3 with R2. What is Q minus P? 0. Q minus P, 5 minus 5 is equal to 0. When 5 minus 5 is equal to what will be Z? 1. When Z is equal to 1, the branch is taken. The branch is taken when Z is equal to Z equal to 1. So it is the branch will take and the control will be transferred to this instruction. So let's assume this is instruction I, this is I plus 1, and this is I plus 2. Instruction J. So if R3 and R2 both are equal, the branch will be taken and the control will be transferred. But in another scenario, now if the contents of R3 is 9 and contents of R2 is 5, what is Q minus P? 9 minus 5? 4. Then
That is 1.
Negative.
That is 0.
Z is equal to 0. The branch will not be taken. The branch will not be taken. And the branch will not be taken if
Is not
0. So which instruction will be executed?
next one.
J. So if the condition is true, the control will be transferred to instruction I100. If the condition is false,
Then it's not.
the control will be transferred to instruction next following instruction. Okay. So the same is true for not equal. So in not equal, so now the decision is now reverted. So in this case, the branch will not be taken for not equal, and in this case, the branch will be taken. And similarly, you can have like a lot of combination in LS and GT. So if we say, let's assume R3 is 9, R4 is 3, and if we say compare R3 and R4, it will compare Q minus P. R3 is greater than R4. VGT label. What will happen? Branch taken or not? Taken. Why taken?
9 is greater.
9 is greater than. And if we say VLS,
Not taken.
not taken. Branch will not be taken. And if we extract the values,
Then same will be reverted.
so actually, what is a conditional jump instruction? So the conditional jump instruction will check the contents of Q and P, and based on the contents of, so actually what's actually happening within the microprocessor. Now this is just like a logical interpretation. This is a logical interpretation of what's happening on the, what's the flow of the instruction from logical understanding. But within the microprocessor, whenever you execute this instruction, compare Q and P, when you compare this instruction, compare Q and P, it will actually change the flags. It will change the flags. And what are the flags? Which flags will be affected? N, Z, C, and V. And based on the contents of these flags, the decision will be taken. Either the branch needs to be taken or the branch, okay? Whether the branch has to be taken or the branch does not take. If the branch is taken, so the control is transferred to the label. If the branch is not taken, the control is transferred to the following instruction. Okay, before understanding all these stuff, that how actually what is going inside a microprocessor, so it can be explained much better with an instruction set encoding. And for this instruction, like explaining this instruction set encoding, we assume a very simple microprocessor. And we assume that this microprocessor supports very limited number of instructions. Okay? Okay. So now, before understanding, then let's assume we have a microprocessor, and within this microprocessor we have 16 registers, R0, R1 up to R15. We have 16 registers within a microprocessor. And so we have different type of instructions. One is R-type instruction, one R-type instruction. What is the format of this R-type instruction? So the format of this R-type instruction is like this: 1, 2, 3, and 4. So this is the output feed, this is RD feed, this is RS1 feed, and this is RS2 feed. And we assume that this instruction consists of 16 bits. Okay, how many bits can be used to identify each individual register? 4 bits. So we need 4 bits for RS2. How many bits for? 4 bits for here and 4 bits for here. And let's assume that we have 4 bits for the output. When we have 4 bits for the output, so it means that microprocessor can now support 16 instructions. If you increase the output size to 5 bits, 32. If you increase the size to 6 bits, 64. So if you increase the size of the output, so it will determine the number of codes that will be supported by the microprocessor. Okay, now RD field. Because the number of registers are 16, so the number of bits required to identify an individual register is 4 bits. And we assume that we are using a reduced instruction set computer, okay, our RISC architecture, and in this architecture we say that we are using register addressing mode. And for this output, let's assume that we have this output. We have microprocessor is supporting this instruction: add, subtract, multiply, divide, maybe logical shift left, logical shift right, and this output is 0, 1, 2, 3, 4, and so on, and 7. So for the R-type instruction is only from 0 to 7. So the instruction will be for type R. The instruction will be of type R with the output range from 0 to 7. Now, if we want to have instructions coding for this instruction, add, R9, R6, R2, what will be corresponding encoding? 0, 9, 6, and 2. This will be encoding. If we have subtract, R11, R12, R0. Subtract, what is the output for subtract? 1. What is the RD field? 11. B. Then C. Then 0. Okay. Now if we say that output range from 0 to 7, it is an R-type instruction. Now another type of instruction.
Why it's limited to 7? 4-bit के साथ हम we can.
We are not only supporting R-type, we also have I-type now. Okay. So actually you can increase the range and something like that. Now we have an I-type instruction, and we assume that now opcode field, now RD, RS1, and hash immediate field. So in this case, so the opcode is 8, 9, 10, 11, 12 and 13. So let's assume this is add I, subtract I, okay, and multiply I also, whatever is this. So actually now in this case, the opcode field, if we have add I, R10, R11, hash 3. So what we are doing now? We are adding 3. Why we are using hash 3? Because it is an I type. I means immediate type. Okay, so now what is the opcode for this instruction? A, B and okay, now in this limitation, what is the maximum size of the immediate operand that we can add? The maximum in this particular example, 15. We can add a maximum value of 15. But if you want to add a larger immediate value, what we need to do? We need to increase the immediate field of the instructions. We need to increase the immediate size of the immediate field of the instructions. Okay? And if you want to increase the number of registers, which field we need to increase? No, number of registers. If we increase, if we say 32 registers,
register fields,
we need to increase the number of bits allocated for the RD field, RS1 field and RS2 field. If we want to support more opcodes, which field we need to increase? Opcode field. Okay, now because this opcode, it is an I type, so if the opcode lies from 8 to 13, the opcode lies within the 8 to 13, it means that now it is a immediate instruction. Now, other type of instruction, J type. In J type instruction. In J type instruction, now we have an opcode and then we have an offset field. Opcode is of course 4-bit and the offset field is now 12 bits. So now, for the sake of simplicity, we assume that now in this J type instruction we have 2 opcodes. So the opcode is now 14 and the opcode is now 15, and it is actually jump JSR. Let's do JSR and return from subroutine. JSR when you want to jump to subroutine, and RHS when you want to return from subroutine. Now, if we call, it's very important. It's very important to understand this concept. If you remember, if we did some example. We did some example in the previous session. We said that let's assume program counter is now pointing to this address A. Let's assume program counter is pointing to an address A, and let's assume this address is JSR label. And label is an address that is pointing to this instruction I1, any instruction IK. It is pointing to an instruction, and this is label. Okay, now program counter is pointing to the address A. What is the difference between this label and address A? Offset. And you want to jump to IK. And IK is actually the address of the first instruction of the subroutine. If I say JSR subroutine is actually subroutine, so this is a subroutine address. JSR subroutine, it will move here. It is the address of the first instruction of the subroutine. So actually, now program counter is pointing here. What is the difference between this? Offset. So actually what will happen? So when this instruction will be encountered, what will happen? What will happen? Your controlled. So actually first push PC. What you are doing? Pushing, not PC. PC plus size of instruction. Now program counter is pointing to this address, to this instruction. When it will jump to subroutine, so you need to store the address of the instruction ij. And what is the address of ij? A plus what? Size of instruction. And in this particular example, what is the size of instruction? No, 2 byte. 2 byte, 16 bits, 2 byte. So actually it is A and it is actually A plus 2. So actually when you are jumping on the subroutine, so first you need to push this address A plus 2 where?
Stack.
On the stack. So actually before this you will push the contents of the program counter plus the size of the instruction on where? Stack. And then PC will be updated. PC will be updated where? No.
जो लेबल जिस पे जंप किया
No, जिस लेवल पे जंप करेगा कैसे जंप करेगा? PC if this instruction JSRC
ऑफसेट एड
ऑफसेट किसके साथ ऐड होगा?
प्रोग्राम काउंटर का जो भी करंट लोकेशन है
All contents of the PC plus offset. This will happen internally within a microprocessor.
Offset, when is the offset calculated?
Offset will be calculated by the assembler or the compiler. The compiler will know the target address. It knows that because whenever this and it's actually knowing the size of each instruction. So these are a lot of instructions. So whatever you are writing there should be done. So I have some very small.
A question. Is it necessary to assign 12 bits for the offset value?
It's not necessary. It's also if okay. Now it means that if the offset is 12 bits, so actually you can jump downward or you can jump upward. So you can maximum have a jump of here 2 to the power 11 downward and 2 to the power 11 upward. This offset will be positive or negative?
This will be negative.
This offset is negative if you are jumping upward, and if you are jumping downward, the offset is positive. So it depends upon. So if you increase the size of the offset bits, so the longer jump can you take. So that's the point. It's not always why I assume a small example just for elaboration. And actually the size of the offset is not 12 bits. Typically it's more than 20 bits, more than 30 bits. Okay, and similarly the output size is not 4 bits. This is just for elaboration.
I was trying to have some correlation within the particular example about the budgeting of these number of bits. Like total number of instructions are only 16. 16.
In this is only for elaboration.
Elaboration.
This is only for elaboration, but if you look at a complex microprocessor or simple microprocessor, it does not support 16 instructions. It supports more than 200 and 300 instructions. Okay, and this architecture is only supporting register addressing mode, immediate addressing mode, and 2 types of jump instruction, not unconditional jump instruction. Actually, it does not contain register addressing mode. Because if we support more and more addressing modes, then it will be more complicated. And that is actually reduced instruction set computing. It does not support. In reduced instruction set computing, what they say, first you can load the data to a register, perform operations on the register, then you store the data into register. So this is called as a load store architecture. It's called as a load store architecture. This is like what is the difference between the RISC computer and sys computer? This is like we will study later on. But this is just for elaboration. And a simple illustrative example. That's the reason. Okay, now I will explain this with. Okay, now if you look at any assembler, so they also know the starting address. starting address from where you will be compiling your program. So let's assume this instruction is called as ORG0000. This means that now whatever the code you are writing downward, the code that you are writing will start at address
0
So it means that now it is the address of the first instruction. At the first instruction. Now let's assume if we have this ORG000 and if we say add, if we have this instruction add R3, R2, R1, sub R12, R10, R5, and maybe add I, R13, R14, and hash 9, and so forth. And then we have J, SR, label, and then maybe. So if you look at this code, small code, so what does it imply? That the starting address is now, what is the starting address? 0000. And if you look at this add, what is the code? 0. R is 3, 2 and 1. Then $0002. Why 2? Because the size of the instruction is 2 byte. So actually it is subtract 1, 12, A, B, C, A and 5, $0004, 13, D, E, and now it is add I. The code of add I, if you remember, was 8. D, E,
9.
and 9. And $0006 JSON label. Now we have some all instructions here and then some instruction. And let's assume this is instruction I100. So what will be this address? 0 plus 99 multiplied by 2, because 99 multiplied by 2 and hexadecimal value. This hexadecimal value. Okay, so this is it will calculate the offset, and that offset will be stored. And what is J? Because it is a J type instruction. It is a J type instruction. If it is a J type instruction, 14. What is the code? E and offset. And offset is actually 0, 1, 2, and 3. It is the offset between the third instruction and the 99 multiplied by 2. So actually the offset will be 99 multiplied by 2 minus 6. And that offset will be calculated here. Okay. Now typically now हो क्या रहा है? Now this is one view. This is one view. यहाँ पे समझ आ गया यहाँ तक? ठीक है? Okay. Now this is your memory. This is your memory, and now we have some microprocessor. So now we have a microprocessor, and in microprocessor has some register program counter. PC. Okay. It has also has some register MAR. MAR stands for memory address register. We have some register which is called as buffer. MBR. It stands for memory buffer register. Now we have some internal register, that is IR. That's called as an instruction register. This MAR is interfaced with the memory, and now we have this memory, which has an address line of A. Address line of A. And now we have a data line of
W.
With address line of A. So what is a program counter? Program counter contains the address of the instruction to be executed from memory. And in this particular example that we did in this particular example, let's assume the program counter is now initialized with 0000. So the program counter, now if you look at the different stages of an instruction execution, it contains an instruction fetch stage, decode stage. Okay, so in instruction fetch stage, what will happen in instruction fetch stage? So in instruction fetch stage, the contents of the MAR will be updated with the contents of the program counter. So what is the contents of the program counter? 000. It will move to where? MAR. MAR will be content 0 0 0 0. It will go on 0 0 0 0 0 0 0 0. Instruction fetch it. You want to fetch the instruction. You want to fetch the instruction. When the instruction is 0 0 and now it's a read operation or write operation?
Read operation.
Read at bar is 0. Which value will move on the data lines?
0321.
This 0321 will go on to MBR. So the contents of MBR will be updated with the contents of the memory that is pointed out by MAR.
That is 0321.
And it will be 0321. Now the first stage is done. That is the instruction fetch stage. Now the next stage is instruction decode.
Decode.
Instruction decode stage. In instruction decode stage, the contents of the IR is updated with the contents of MBR. What is MBR? Memory buffer register. What was brought in here? 0321. Now the instruction register contains the instruction to be decoded. Which field of the instruction will be checked?
Opcode.
Opcode field. What is opcode field?
0.
0. How does it determine what type of instruction is it?
ये वो
And
I type.
Which type?
I
R type.
R type. Yes sir.
R type. So R type. So when it is R type, so instruction decodes to code. We say, oh no, it is add instruction. What type of instruction is this?
R type.
R type. Okay, this is an R type. Oh, so we need to add. What we need to add? 2 registers.
2 registers.
So there is some ALU. We have some temporary register A, temporary register B, and now you have an ALU. And for this ALU, the output field is done. So we say that now we need to add. The instruction is decoded. Now we need to fetch the operand. We need to fetch the operand. So it means operand fetch stage. The next stage is operand fetch. If this is an R type instruction, what are these operands stored in? Where they are stored in?
प्रोसेसर के रजिस्टर्स में.
Processor registers means which registers?
Data register.
R1
and R2.
R2. So it will check the RS1 field
Yes.
and RS2 field. So RS1 field will go to A, RS2 field will go to B, and the contents of RS1, not RS1. The contents of RS1 and RS2. Now let's assume that the contents of, now we are adding R2 and R1. Let's assume the contents of R1 is 5 and the contents of R2 is 3. So that value from R1 and R2, 3 and 5 will be loaded into this. So actually in this operand fetch stage. So for operand fetch stage, so we assume that there are 2 temporary registers A and B within the microprocessor that are attached with the ALU. So actually what will be updated in A? RS1 field. The contents of RS1, not RS1. Because RS1 is 4-bit field. And the contents of RS1 means the contents of that register. And if we assume that that register is 16 bits, so it is a 16-bit value. And then we will be uploaded with what? Contents of RS2. So this is in operand fetch stage. Instruction fetch stage, instruction decode stage, operand fetch stage. Now we will execute this instruction.
So in this case, A and B are also registers. In this case,
A and B are internal registers within the microprocessor. That is not visible. That is not visible to the programmer. It is not visible to the programmer. Basically, if you want to perform these operations, so you need to load this data. So you need some latches, flip-flops, buffers, or something like that. When you need this flip-flop, so actually they are internal registers that are not visible. So first they are read, and when it's read, so it will perform the operation and store in some register C. So it will execute the instructions of C. How C will be computed? The contents of A of B. And what is the outfield here? Add. For subtract it will be minus. And then we execution. Then another stage is the operand store phase. In the operand store phase, the contents of this C is now written into the register. Which registers?
external register.
RD field. So RD is updated with the contents of what? So now this is an. But before doing this, microprocessor should point to the next instruction. So when it should point to the next instruction, so you can do this in the instruction decode stage because it's done. So now you can update up to PC. PC is equal to PC plus size of instruction. When it's PC plus size of instruction, and then if the size of instruction is now 2, so it will now point to 2. Point to 2. Go to memory. Do the same steps. And the same fetch. Instruction fetch, decode, operand fetch, instruction execute, and operand store. And then this. And in the second phase, if you look at this, this is an add I. So now the instruction fetch state, now an add I. So now you have, let's assume 4. MAR is now 4. What is the data now? 8DE9, 8DE9, 8DE9. Add means add, but add I, not register. So what will be loaded in the operand fetch? A will be RS1 and B will be what?
9 immediate value.
The immediate value. But immediate value is now 4 bit. The register is now 16 bits. Register value is now 16 bit. And now you are adding. So now B will be immediate value with sign extension. Why sign extension?